Hey guys, this is Mrs. Steele here with you for our last practice problem from the Chapter 5 review from our textbook. So now we're going to cover a Dalton's Law kind of question pertaining to two gases that were originally separated from each other that were allowed to expand to completely fill both ends of this little flask contraption that we've got here. So let's look at the actual wording of the problem. So number 85 from Chapter 5 review says, consider the flask in the following diagram. What are the final partial pressures of hydrogen and nitrogen gas after the stopcock between the two flasks is opened? Assume the final volume is 3.00 liters. What is the total pressure in torr? So when you look at this problem in the textbook, of course, the drawing is a little bit prettier probably than mine, but bear with me. It also provides some given information here. It says that over on this left-hand flask, the larger flask, this is where the hydrogen gas was contained when the two gases were separate. And you had 2.00 liters of hydrogen gas. It also shows that there is 475 torr of pressure that has built up because of the presence of that hydrogen gas. Now, over on the other side, actually I'm going to go ahead and draw some hydrogen in here just to kind of give it some effect. And keep in mind, technically these are diatomic, but I mean, these are so small, just pretend. All right, got it. Boom. Now, over on the other side, we'll have nitrogen gas. And just for effect, I'll draw these as a different symbol, just so that we have something to look at here. It says we have 1 liter of nitrogen gas in this right-hand flask, and it is exerting a pressure of 0.200 atmospheres. Okay? All right. Let's look and see what other helpful information we might be able to glean. Oh, if we look at the problem, it says the final volume, once you release the stopcock and allow the gases to flow from either end to, or from one end to the opposite end, it says that the final volume is 3 liters. I feel like that's super important to write down, that there's no unusual variation in volume. Essentially what happens is the gas particles, once this is open here in the center, the gas particles can flow to the other side and they will occupy both sides of the flask uniformly, we'll say. So I'm just going to write that down. The final volume will be 3.00 liters, which if you look at the initial volumes when they were separate, it makes sense that they're going to expand to 3 liters. Just add them up. A couple things that don't appear to be mentioned in the question are temperature or number of moles. So I think it's safe to assume if they're not mentioned and there's no indication that any type of chemical reaction is taking place, that the number of moles is constant. It's fixed for both. I think it's also safe to say, since there's no mention of temperature, that the temperature remains constant as well. Why does that even matter? Let's go down a little bit. This problem is asking us to solve for the total pressure, right? Total pressure. And they even specify what unit they want the final answer to be in. So make sure you always check to see if the question is requesting that the final answer be in a particular unit. If you look at your AP equation sheet, you may notice that there is a gas law that will help us when we have two different gases that will spread out to occupy the same volume. Dalton's law says that the total pressure inside of a container is equal to the sum of the partial pressures. So for example, in our case, the partial pressure of hydrogen and the partial pressure of nitrogen gas. that they exert independently. So we just take the sum of those to get the total pressure. That sounds easy enough, but I have a few issues here. The information that's provided here for both chemicals, these are the initial conditions. And they seem to mention that the volume changes, so there's a final volume that each of these takes up. Let me put it to you a different way. When you have a problem where you've got a mixture of gases involved, but they started out separately on opposite ends, as what you see here, I recommend that you consider the gases separately. Like when you do your calculations, don't try to blend them together just yet. Try to think of them as independent entities, because that's what they are, since there's no chemical reaction currently taking place. Okay? So for example, the partial pressure of hydrogen gas at the end of this little situation, or this little experiment here, is present once the hydrogen gas, once the it here is hydrogen, occupies both ends of the flask. Let's go up to the drawing and let's just illustrate that. And I'm going to actually get rid of the nitrogen for a second, just so you can picture what's going on here. So initially, you just have hydrogen on the left, and then once again, remember, I'm going to open up this little valve here, and when I do, some of our hydrogen gas will start to flow over here. And of course, keep in mind that it's always in motion. So there's just going to be this kind of regular, erratic, random motion of particles, but eventually they will start to expand to occupy both ends of the flask. So I had an original volume, V1. I had an original pressure, P1. I want to know the final pressure of hydrogen gas. That sounds like a P2. And I do know the final volume, which was 3 liters. If I look at this carefully, this looks a lot like combined gas law, except without the temperature, because temperature is constant, right? We already addressed that. It's not mentioned in the problem, so I don't really need that. So I can just take that out to make the problem easier to understand. So now that I've addressed that, let's solve for the final pressure, but keep in mind this is just for hydrogen gas once it expands to occupy both ends of the flask there. So I'm going to rearrange the equation to solve for final pressure for hydrogen gas, and I get P1 V1 over V2. And what I can do is just substitute in the numbers that I have. Let's go back up and take a look. I've got the original pressure and the original volume, so let's put those in. 475 torr times 2.0 liters. And then I'm going to divide by the final volume, which was clearly mentioned in the question as being 3.00 liters. Check that in your calculator, and you end up getting 317 torr. Now, have we answered our question? Let's go back up and look. We're trying to solve for the total pressure, not just the partial pressure of the hydrogen. So this right here is the partial pressure of the hydrogen at the end of the reaction. So what else do we need to do? I need to repeat this calculation, but this time I'm going to solve for the partial pressure of nitrogen gas. So I'm going to go back and I'm going to kind of pretend for 2 seconds here that the hydrogen gas doesn't exist, and let's just look at this from nitrogen's perspective. Okay. Trying to erase all the hydrogen. Easier said than done. There we go. Now, the nitrogen, I drew them as X's just to contrast with the hydrogen. No real reason besides that. So, remember it was completely sealed off originally. So, initially the nitrogen was only occupying a volume of 1 liter and was exerting a pressure of 0.2 atmospheres. I'm going to release this, open up the stopcock, and some of these gas particles are going to start to move this way. Okay. And this is going to happen, with time, gradually. It's going to, just due to that kind of random motion of the gas particles. But with time, they're going to start to make their way. Eventually, they will spread out as kind of homogeneously as they can. So you might have kind of a good proportion of gas particles on each side. They're now expanding, they're filling up 3 liters total, because it's not just the 1 liters on this side, but also the 2 liters on the other side. So that's a total of 3 liters in our final volume. Long story short, you're going to do the exact same type of calculation. You're going to solve for the final pressure. Okay. And we're going to use P1V1 equals P2V2 again. This time I'm just going to use the data for nitrogen gas. So go back up, and the pressure is 0.200 atmospheres. Keep those numbers there. Sig figs matter. And then the initial volume for the nitrogen gas was 1.0 liters. 1.00 liters. And then at the end of this little experiment, the nitrogen gas occupied both ends of the flask, and so that would be a total volume of 3 liters. Check that in your calculator, and you end up getting what seems like a really awkward answer, 0.0667 atmospheres. And I want to pat myself on the back, but I still haven't answered the question, which was to solve for total pressure. But I'm getting really close at this point. Okay. I'm going to take my answer that I just got in atmospheres, and since I know that I need to get my answer in torr, I'm going to convert that one from atmospheres to torr. I need to do that right now. So I'm going to do that. 0.0667 atmospheres. If I look at my AP equation sheet, I notice that for every 1 atmosphere, I have 760 torr. Check that in your calculator and you get 50.7 torr. Okay. So we're almost done. Let me insert one more page. Okay. Whoops. Let's try that again. There we go. I'll do it right here. So in conclusion, now that I have my partial pressures of hydrogen gas and nitrogen gas, I can combine them together, 317 torr plus 50.7 torr, and I get a final answer of 368 torr. Some of you might be wondering, why did I not include the 0.7? Well, if you remember, according to sig fig rules, when I'm adding 2 measurements together, I have to end my precision at whichever measurement had the least amount of precision. So while the calculator answer is 367.7, when I end my precision at the ones place, this 7 here causes that 7 to round up. So that's how I end up with 368 torr. So to answer the question, once these two gases mix in our flask to occupy a total volume of 3 liters, their combined pressure will be 368 torr. I hope that this was a helpful explanation for how Dalton's law applies when you have a combination of gases at a constant temperature and number of moles. Thank you.